Hi, everyone, and welcome back. We have another talk and two presenters. It is Shah and Vijay Ivaturi, and they're coming from Julia Computing and the University of Maryland, respectively. So welcome. I'm excited for your talk.
Thank you. You need to share your screen. Full screen mode, Viral?
Yes, I'm just switching to that. Thank you. All right. Is it? Can you see me in full screen, or rather my slides?
Yes.
All right. So thank you all for having us, and we've been excited to be invited to the R in Pharma conference. Of course, the topic of our talk is Julia in Pharma, but as we jump in, you'll see how these two systems complement each other. So I'm Viral Shah. I'm the CEO and also co-founder of Julia Computing and one of the creators of the Julia language. And we have with us Dr. Vijay Ivaturi, who teaches pharmacometrics at the University of Maryland in Baltimore and is also a co-founder of Pumas.ai. Why did we create Julia? Just jumping in right there, right? I think all of you must have experienced, that, hey, it's nice to write algorithms in R, but you do not get performance. And so you end up using RCPP in order to get performance, right? And this is what we sort of termed as the two-language problem, that you develop in one but deploy in the other. And that leads to a lot of challenges in terms of workflows, in terms of teams, in terms of communication, and in just terms of what is possible. And this was how we started the Julia project almost 11 years ago. It all started with an email thread about a new language in 2009. Here I have pictures of all my co-founders, the four of us who actually started the Julia language back there. If you see anyone on LinkedIn who says 15 years of Julia experience, you know that that is simply not possible. The highest you can have is 11, which is me here. And in 2012, we actually announced the project to the world with the Why We Created Julia blog post. And then a wonderful thing happened. We saw a couple of folks from our community get seriously interested and jump into Julia development. John Miles White wrote the well-known Julia I Love You post, and Doug Bates had a post on the Julia version of a multinomial sampler. And it has been a multi-year journey since then, integrating a lot of statistical capabilities. We integrated RMath in 2013. Distributions.jl came along, GLM.jl came along, and a lot of this was actually done by Doug Bates very early on. And since then, we have a lot more integration with R that has happened. But let me come back to Julia a little bit. So in 2018, we released Julia 1.0. Last year, we were awarded the Wilkinson Prize for Numerical Computing, the Sidney Fernbach Prize for Supercomputing. This year, we are at 20 million downloads. We'll talk a little bit about Pumas.ai, and also we just released Julia 1.5 with a boatload of new capabilities. Over 10,000 organizations are using Julia today, and many of them include some of the pharma companies. Many of you who might be actually seeing your firms represented in this slide here. It's being taught at over 1,500 universities that we know of. Taught at and research and used for research. So over 1,500 universities. Julia is showing up in all the language rankings now and is rapidly climbing. The IEEE Spectrum ranking, which I think is one of the better rankings out there, put Julia at number 19 this year. And Nature magazine sort of had a nice feature on Julia. This was, I think, last year, saying come for the syntax and stay for the speed. And it really talks about all the amazing scientific and HPC applications that are being enabled by Julia today. There are several books on Julia and several courses that are teaching Julia. Just about everything. I do not yet have on this slide a book on statistics with Julia, which is just it's in the progress of being published. But there is a very detailed a Julia stats book that is coming out very soon. And while Julia sort of does a lot of the traditional HPC and numerical computing tasks very well, it also is at the forefront of modern AI and differentiable programming, which we believe needs its own language. That Python is not the right language for expressible machine learning computations. And here I just have a couple of Twitter threads from Jeff Dean at Google and Jeremy Howard of Fast.ai. And I'll urge you to sort of come back to these slides maybe a little bit after my presentation. They'll all be uploaded. So without further ado, I'm going to request Vijay to talk about Julia in pharma.
Yeah, thank you so much, Viral, and thank you to the Pharma, the R in Pharma organizers for inviting us. So everybody who's attending this conference pretty much have been beaten down to death with this particular workflow in the pharma, where we go from discovery to post-approval. But the point about what I'm trying to make in the slide is, if you look across in each section, there are varied analysis that are required along the drug development pipeline. And these various analysis, especially in the context of quantitative sciences, the modeling and simulation aspects they go all the way from preclinical to post-marketing, right? So there's a lot of complexity and a lot of moving pieces that need to be brought together. Next slide. And the idea here is that if you break that each of these projects into different buckets, data wrangling, data analysis, scenario planning, and trying to project what's going to happen, and then finally reporting and regulatory submissions, if you look at the ensemble of tools that are used to get us to that final point of submission, it's just not one. We have SAS, R, Excel, Fortran, all of these have and are still doing a fantastic job, but the cost of interoperability is really high. The result being that quantitative clinical pharmacology is still a very, very niche field. We are not able to gain more entries, folks to come in, because we're not able to democratize the tools. And one of the goals of why we started this journey in Julia is that we wanted to make this transition smoother. How can we get to a system that allows easy interoperability? And let me point one specific thing here. Over the last 8 to 10 years, and I've been in this field for a while now, over the last 8 to 10 years, R has really made these workflows efficient. The interoperability has become much more easier because of R. And before that, you couldn't just imagine stitching all these different tools together to make it work, right? So while R is doing a fantastic job in trying to sit on the top and trying to stitch different pieces together in the computational side, what we are doing in the Julia and Pumas world, next slide, is to be able to integrate the scientific computational part. So there are statistical parts that R is, the statistical and reporting parts that R is doing a fantastic job of putting together and trying to interoperate, while Julia is coming in from the back and stitching across all the scientific computational tools that are required. And Julia has an excellent interoperability with R, and I use it on a day-to-day basis, and it is important that Julia and R coexist, and together it's a fantastic ecosystem that can grow. Next slide, please. And as Viral talked about, statistics in Julia not as mature as in R yet, but is catching up very quickly. And we have everything from really fantastic data input and output packages to core statistics that are available, and some of the best-in-class probabilistic programming languages that are out there in terms of Turing and advanced HMC. Next slide. So one of the aspects that I want to talk about is recently we've done a complete regulatory submission in Pumas and Julia together, 100% Pumas and Julia, that was accepted through the MIDD program. And this is a win for us, that Julia, and just like in R has taken its time, but it is production ready. R is being used everywhere in regulatory world, right? So we are also production ready in terms of Pumas and Julia. And recently we had a submission that was approved, and we have a few other submissions that have already been reviewed as we speak in terms of the ecosystem. Next slide. A few key highlights that I just want to point out. This year, so we've launched Pumas and Julia maybe early this year, and since then 450 pharmacists have been trained in using Julia and Pumas, and obviously along the way always R coexists. It doesn't exist in silo. R is always taught because R is a while R is a lingua franca for reporting and for the front end parts. Julia has become the lingua franca for scientific computing in the backend for us. We have more than 40 pharma companies that have taken up and are using Julia and Pumas in their workflows. And we have sped up, and Viral is going to talk about this a bit. We have worked with Big Pharma to speed up the multi-scale models by more than 200 to 300x, right? And Julia is the first one to be able to run on GPUs in this space. Lastly, even University of Maryland and 6 other academic institutes have completely shifted the training programs from what we had before to Julia and Puma. So I'm really excited about this opportunity that Julia has brought in from a backend perspective, and its marriage with R will really propel us to go forward. And Viral will take us to the next few slides. Viral.
Thank you. Thanks, Vijay, for bringing that whole, how Julia works in the pharma domain, that whole sort of domain experience into this talk. And I hope that the listeners sort of, can appreciate that not only is the Julia world focusing on HPC in general, but also is deeply focused in the world of pharma. This is a quick slide I wanted to showcase one of the products that we are putting together, which is Julia Hub. So Julia Hub and Pumas is a complete cloud-based, browser-based workflow for pharmacometric computing, and it is a commercial platform. It has all the regulatory compliance, supports polyglot workflows, GPU acceleration, and everything. So everything that you've seen talked about on these slides so far, and what's going to come next, are is possible to sort of integrate and sort of execute on the Julia Hub workflow in your organization, whether you're a 2-person small consulting shop or one of the largest pharma companies out there. This is one of the most exciting results that I would like to share. This is a speed up of 175x. Subsequently has been increased to 300x now, with even more improvements for multi-scale QSP models. This was actually a project that we did with our colleagues at Pfizer, and it was a project that involved Ted Reiger, Anna Scher, CJ Musante, and all the folks at Pfizer, working with myself, Chris Rakakis, Yingbo at Julia Computing, and then Vijay at Pumas AI. And we really brought together sort of all the tools out here and ran it on the Julia Hub platform to get these speedups. But some of these codes were in MATLAB, some of them were using sundials for their ODE solver, some of them were in C++. But across the board, what we saw is that Julia brings a significant improvement. Over and above that, you get parallelism through Julia's multi-threading, you get GPU acceleration, and then you can go to clusters. And all of this is possible with only a few lines of code being changed as you go along. This was also the Best Abstract Award, or rather it will be now the Best Abstract Award at ACOP 2020 in the next couple of weeks. And so we are really excited about, about that recognition. Another example that I have is, the Gillespie algorithm. So this is work by Simon Frost, who has subsequently been working after he published this on SIR epidemiological models, I believe, at Microsoft Research now. And we have a collaboration at MIT on many of these kinds of models. But what this particular paper went to show was that there was a Gillespie SSA algorithm implementation in R that gave you about 894 milliseconds per simulation. Native R would have been about a little bit slower. RCPP was significantly faster, like by a factor of 1,000. There is a Julia-based Gillespie.jl package that is a pure Julia port of the R package that brings it down to 4 milliseconds. But then if you use the deeply high quality differential equations.jl package that Chris Rakakis wrote, you can actually get higher performance than RCPP. And this is something that I really like to show that, hey, when you remove the barrier of language, even a domain-specific person who does not otherwise work with C++ can get C++ levels of performance. And this is truly what sort of defines, what Julia started out to do, set out to do, and we're so glad to see it happening today. Calling R from Julia. So Vijay talked a lot about the interoperability, and I have a couple of slides here. So this is calling R from Julia. There is the Julia R call package. And here's an example where you're calling a ggplot, you're making a ggplot call from within Julia and plotting a data set using ggplot. Especially if you install the rcall package, then at the Julia terminal, when you press the dollar sign, it will actually shift, it will actually drop you into an R REPL. So you can sort of in the same interactive session go back and forth as well. But then often, people want to go the other way, right? That, you have your entire workflow set up in R, but maybe you just want to call a few Julia libraries. And for that, there is the Julia call library that is registered on CRAN. And, Doug Bates uses this to call mixedmodels.jl. He gave a talk at JuliaCon, that's the YouTube link right here, which talks about, sort of, as he was sort of trying to overhaul LME4 for the next generation mixed models package, he found that just writing it in Julia gave him orders of magnitude more performance, and then he demonstrated how you can call it from within R. And similarly, Chris Rakakis has made all of his GPU-accelerated ODE solvers available in R, really sort of proving the point that Julia is the true language of libraries, that you could write it in Julia, be completely, make it available in everything else, but you could also, have a complete Julia-based workflow as well. One of the exciting things that we've seen here in the Julia world is new kinds of UIs. So in the R world, Shiny has made a tremendous impact in how data scientists and statisticians and high-performance computing users think about sharing their results with their colleagues. And in Julia, we've had sort of interesting developments. This is the Pluto notebook. It's sort of, these are reactive notebooks. So if you change a cell that other cells depend upon, everything, all the dependencies get updated. And this is what Pluto does. And I would urge you to check out the JuliaCon 220 talk on Pluto right here. I will move on. Julia is very good at processing large data sets quickly. If you see this little blue line out here, this is the Julia part. And each of these have two numbers, the compilation time and the running time. This is a fantastic benchmark put together by H2O.ai. And often people find that, just loading Julia up on a large multi-core machine with tons of RAM leads them to be able to process large data sets without having to switch to a distributed computing system like Spark, or even going across several nodes. So these are 50 GB group by operations that Julia does incredibly well on. Excuse me. Data science operations, loading data with CSV files, Julia turns out to be significantly faster, and a lot of that is because of a very high quality native parser in Julia, but largely also due to the fact that Julia has native multi-threading, which means that the CSV parser in Julia was natively multi-threaded. Julia's data frames package has not yet been multi-threaded, but that is happening as we speak. A lot of traditional machine learning packages are available in Julia. The typical thing people like to compare against is scikit-learn, and we have all the right pieces. For deep learning, Julia uses the Flux ML library, and it provides a sort of a Keras-style implementation, Keras-style syntax. With a lot of the common pre-trained models available. You can also call TensorFlow and Torch kernels directly from Julia. But the reason why people come to Julia for deep learning is because if you're not doing the standard models, it is extremely hard to sort of program in TensorFlow. And this is where people really like to use Julia's Flux models. A lot of image processing, a very nice image processing ecosystem with images.jl. It's also being taught in a computational thinking class at MIT this semester with, and the real exciting thing is that it's being taught by 3 Blue 1 Brown, Grant Sanderson, who many of you might know as the author of some of the best math videos on the internet. A lot of optimization capabilities in Julia with Jump and Optim, all your linear solvers and quadratic solvers and so on and so forth. A fantastic scientific machine learning ecosystem in Julia that builds on top of all the ODE solvers that we talked about, and that is the underpinning of combining pharmacometric analysis in Pumas with modern deep learning capabilities. And this is exciting new work that is ongoing, and we'll be happy to share more in a future talk. Julia has some of the best probabilistic programming capabilities available. I am told that these are rivaling Stan right now, but I'm not a user of these things, so I would not be able to get into detail, but I would encourage you to find the Turing.ml website and go through their paper and their benchmarks. The syntax is actually really familiar to anyone who's writing math and stats syntax. And Richard McElrath talked about sort of porting his book and various things over to Julia. And as he says, not yet encouraging his students, but he's using it a lot more already. So with that, I thank you. Julia Computing and Pumas.ai, both companies out here are available to interact with you guys. If there is commercial support, if you'd like to bring Julia into the enterprise, if you'd like to install Julia Hub. And with that, I will maybe take a couple of questions if there is time.
I see that Vijay has been doing a great job answering questions on the spot. So I think that if there are any questions left, they will be diverted to Slack, to the Slack channel. And thank you both for a great presentation.
Thank you. Thank you, everyone.
Thanks.